Greetings. This video is for Calc 2, section 7.7, and we're talking about specifically the midpoint rule. So the midpoint rule can be used as an approximation for some integral from a to b. We're going to work on a specific example with y equals x squared on the interval from 1 to 4. So we're looking for the area underneath the curve of y equals x squared from 1 to 4. So of course we can set up that integral and evaluate it and find that that's equal to 21. But let's use a midpoint approximation rule to get an approximation for that same integral and see how we do. So the idea is we're going to take this area in yellow and divide it up into n subintervals. I'm going to choose 3. So here's 1, 2, and 3 subintervals. And what we're doing with this approximation is we are forming rectangles, and when we find the area of a rectangle, which we know how to do, the area is equal to the base of the rectangle multiplied by the height of the rectangle. So we're going to do that for 3 rectangles. And we're going to add all 3 of those together, and that's going to give us an approximation for the area underneath the curve. Now the first thing I want to point out is that my base of the rectangles is the same. So this base for each of these rectangles is exactly the same. And the reasons it's exactly the same is I've chosen the width or the base to be exactly the same on the interval of x. So this would be, if I filled in the rest of the numbers, this would be 2, this would be 3, and we already had 4. So the base is equal to 1 in this particular example for each of my rectangles. We refer to the base mathematically as the change, so base equals the change in x, or delta x. So the width or base of my rectangles is delta x. And then the height of my rectangles. Well, I have lots of places to choose from on where I want to say approximate the height of this rectangle. Do I want to do it at the beginning? Do I want to do it at the end? Or do I want to do it someplace along the curve, say here? And we have lots of choices. But M, the midpoint rule, stands for we're going to choose the height of each of these rectangles approximating the area to be at the midpoint of each sub-interval. So this would be midpoint 1. So this was height 1 and midpoint 1. This would be midpoint 2. So midpoint 2 and height 2. And this would be midpoint 3. Midpoint 3 and height 3. If I sketch out what those rectangles look like, I choose the midpoint to be my height approximation for each of those 3 rectangles. And what I would have is this rectangle 1 plus this rectangle 2 plus this rectangle 3, and add those all together. And that would equal an approximation to my area underneath the curve. Now, one thing I want to point out here is it's easy to see that this is not an exact because I overshot a little bit here, here, and here. I've overshot the value. But I've undershot the value in these 3 places. So it's not an exact approximation, but it's close. And the question is, well, how do I get closer and closer? Well, as it turns out, if I let n be the number of subintervals, as n increases, the error of approximation gets less. So as these subintervals get smaller, I have more of them. So the width gets smaller, but the number of them gets bigger. Then I have less and less error. And in fact, if I let n go to infinity, and I have this m sub n, so n goes to infinity, so I have infinitely many number of subintervals, then I no longer have an approximation, I have an exact value of the area underneath the curve, or an exact value of the integral. So the midpoint rule, written out algebraically, is doing what we've drawn up here in the picture. I'm taking the value of the subinterval at its midpoint, and I'm plugging it into the function and figuring out what the height is. That's what these mean. Each of these spots in my algebraic notation. Then I'm adding all those together. So each of those areas will have a delta x being multiplied, a delta x being multiplied. So I'll have base times height plus base times height plus base times height. Well, the bases is the same in each one. So I'm factoring out the bases and summing up all of the heights of the midpoint. So I could do it by distributing the delta x to each one, but algebraically it's much easier to sum up all the heights and then multiply by the base one time. So how do we find this delta x? How do we find the midpoint? Well, we take b minus a and divide it by the number of subintervals. That'll tell us the width. This will be the width of a rectangle, or sometimes I've been calling it the base of the rectangle. And then how do we find the midpoint value that we're going to plug into our function to find the height? Well, that's 1/2 the end values. So the midpoint is a halfway between sum up the mid values and divide it by 2. And it gets this notation of x bar because that's a math notation for the standard average. So I add two things together and divide it by 2. All right, so let's look at this example and actually work it out using numbers instead of the picture. So once again, I have this y equals x squared from 1 to 4, and I want to do 3 subintervals, so n equals 3. So my delta x is equal to 4 minus 1, or b minus a, divided by 3. So 3 divided by 3 is equal to 1. And then I like to make this little chart so that I don't forget what I'm doing. So I started with x naught. So I'm starting here with x naught. And so x naught equals 1. And then my x1 equals x naught plus how wide I want my base to be, or delta x. So in this case, that's 1 plus delta x, which is 1. And so that's a total of 2. Then x2, I'm going to start with x1 and then add over how wide I want my base to be for a total of 3. And so x2 is equal to 3. And then x3 is starting with x2, and then how wide do I want my base to be? I want it to be 1, so that's equal to 4. So my x naught is 1, my x1 is 2, my x2 is 3, and my x3 is 4. So then I just need to figure out what are the values for this x bar sub I. or these input values that I'm going to put into my function to figure out what the height is? Well, that's 1/2 and then the endpoints of the interval. So I have 1/2 x0 plus xi, so that's 1/2 times x0, which is 1, plus x1, which is 2, and this is 3/2, which is the same as 1/2. And then the next one is 1/2 times 2 plus 3, so that's 5/2, and so that's 2.5. And then finally, I have 1/2 times 3 plus 4, which is 7/2, and that's equal to 3.5. So these are the values. If I put these up on the picture that I drew before, this would be 1.5, this would be 2.5, this would be 3.5. And I'm going to put them into the function x squared to figure out the height for each of those rectangles. So when I'm writing this out, then my m sub 3 is equal to delta x, which is 1, times f of 1.5 plus f of 2.5 plus f of 3.5, and I add all those together. So 1 times f of 1.5 is 1.5 and square it, and f of 2.5 is 2.5 and square it, because I'm putting those values into my function, and then 3.5 and square it. So when I do that in my calculator, I get 1.5 squared is equal to 2.25, and 2.5 squared is equal to 6.25, and 3.5 squared is equal to 12.25. So then I just add those values up. So I get 2.25 plus 6.25 plus 12.5. When I add all those values up, I got 20.75. So the way I would write this then is my M3 midpoint rule with 3 sub-intervals is equal to 20.75, which is an approximation of the integral from 1 to 4 x squared dx. Okay, hope that video helps as to what's actually happening with the midpoint rule, and this has a powerful application in many of the STEM fields.